This discussion is brought to you by PhD Light. All right, so strap in, because today we're going deep on something pretty wild. Terraforming Venus.
Venus, huh? You sent me a paper claiming to have a plan for that color me skeptical.
Well, that's why you're here. We've got this research paper that lays out this surprisingly detailed roadmap for turning Venus, from that scorching inferno into like a potential paradise. It's crazy.
Right now, Venus is it's a furnace. 460 degrees Sealy lead would melt. And that pressure, 93 times Earth's. That's like imagine being 900 meters deep in the ocean.
Yeah, and don't forget that atmosphere, practically pure CO2. It's like a runaway greenhouse effect gone wild.
But for sure, totally. It's like Mother Nature's pressure cooker, just pop the lid.
Exactly, and that's where I see the first problem. The paper, it suggests cooling Venus down using a giant space mirror.
A giant space mirror. All right, I'm intrigued. But how?
Well, that's the thing. The concept, it's interesting, but let's look at the energy balance equation. Pin equals parenthesis 1 minus A, close parenthesis times S times pi times R squared.
Okay, for those of us who haven't cracked open an astrophysics textbook lately, what does that even mean? Basically, imagine you're trying to block out the sun with like a beach umbrella. Sure, you get some shade, but you're still getting cooked. To really cool Venus down, you'd need a mirror system so huge, so perfectly positioned, it's basically impossible with what we have now.
So the giant space mirror, it's a no-go.
I wouldn't say no-go, more like, whoa there, hold your horses. The engineering would be insane. And even if we could build it, keeping it stable, keeping it precise for centuries, another massive problem.
Okay, point taken. But let's say, just for fun, we could cool Venus down. What about that insane CO2 atmosphere? The paper mentions lasers sequestration, even launching the frozen CO2 into space.
And that's where we hit another mathematical wall. Let's take the mass driver idea, shooting frozen CO2 into space. The energy you need to escape Venus's gravity it's given by KE equals B.5 times M times V squared.
Oh boy, here come the equations.
Where M is the mass of the CO2 and V is the escape velocity, which for Venus is about 10.36 kilometers per second. Now think about the sheer mass of Venus's atmosphere, roughly 4.8 times 10 to the 20th kilograms.
My brain's already hurting just thinking about those numbers.
Well, to launch that much mass, even in pieces, you'd need a ridiculous amount of energy. We're talking multiple nuclear reactors running nonstop for decades, maybe even centuries. It's just not doable, not with our current tech, not with the energy we can produce.
So even if we could cool Venus down, getting rid of that CO2, another huge problem.
Let's just say it's highly unlikely. Think of it like this. Trying to empty an Olympic-sized swimming pool using teaspoons. Could you do it? Technically, yeah, but it would take forever, and the effort, it's just not practical.
All right, so 2 strikes. The space mirror, huge engineering hurdle, launching CO2 into space, energy nightmare. Anything in this paper that doesn't make you grab your calculator and despair.
Well, they do talk about importing water from Europa to make oceans on Venus. It's creative, I'll give them that. But again, the logistics are, well, mind-boggling is an understatement.
Yeah, and we're not talking about like shipping a few bottles of Evian, right?
Yeah.
This paper is talking about carving out huge chunks of ice from Europa and launching them towards Venus.
Yeah.
How much ice are we even talking about? How do we even move it that far?
The paper, it's a little fuzzy on the details, but to get oceans on Venus, like the size of Earth's oceans, we'd need to move an insane amount of water. Something like 1.2 times 10 to the 21st kilograms. It's almost too big a number to even grasp.
Okay, I need an analogy here. Something to help me wrap my head around this.
Imagine trying to fill the Grand Canyon with ice cubes, using nothing but buckets and people passing them hand to hand. That's basically what we're talking about.
Okay, that's a lot of ice cubes.
Yeah.
And even if we could somehow get that much ice off Europa, how do we keep it from melting on the way to Venus? The paper mentions something called space tethers.
Yeah, space tethers. It's basically a long, super strong cable using physics and orbital mechanics to move stuff around in space. The idea is you have one tether attached to Europa, one attached to Venus. The Europa tether, it flings the ice towards Venus, and the Venus tether catches it, slows it down so it doesn't just smash into the planet.
Okay, so like a cosmic game of catch.
Yeah.
Except instead of a baseball, it's chunks of ice the size of mountains.
Right. It's a cool concept, no pun intended. But let's get back to the math. The strength a space tether would need to launch and catch these massive ice chunks would be unreal. We're talking materials way stronger than anything we've ever made.
So back to material science being the bottleneck.
Exactly. And even if we somehow invented these super strong materials, the tethers themselves, they'd have to be ridiculously long, thousands of kilometers. Putting them up there, keeping them working, with all the space junk and radiation, it'd be a nightmare. And then there's the energy to power the whole thing, launching the ice, catching it, adjusting the orbits. We'd need as much energy as the entire Earth uses for decades.
So space tether's cool idea, but not really solving our water problem anytime soon.
Hmm.
What about the other stuff the paper brings up, like that crazy long day-night cycle on Venus? They suggest more orbital mirrors to create artificial days and nights.
Another good idea on paper, incredibly tough in reality. Venus rotates so slowly, one day-night cycle takes over 116 Earth days. To make it more like Earth, we'd need mirrors directing sunlight to certain parts of Venus while shading others. The precision, the control, it's way beyond what we can do right now.
Like trying to adjust a giant dimmer switch for a whole planet.
Exactly. And then you have to keep those mirrors working out there in space, getting hit by micrometeoroids, blasted by radiation, keeping them operational in the right spot for centuries. That's another huge challenge.
It seems like every solution in this paper just creates a bunch of new problems, like a puzzle where every piece you fit in opens up another empty space.
That's a good way to put it. And it leads us to maybe the biggest challenge of all, introducing life to Venus. The paper suggests, starting with cyanobacteria, those tiny organisms that helped oxygenate Earth billions of years ago.
So we're basically trying to create a whole new ecosystem on Venus from scratch. Isn't that super risky?
Yep.
What if the cyanobacteria change or cause some kind of ecological disaster?
That's a valid concern. And this is where what we know about astrobiology and ecology kind of hits a wall. We've never done anything like this before. Never tried to engineer an entire biosphere from the ground up.
Like a chemistry set, but planet-sized? Lots of potential for things to go wrong.
Exactly. And if something goes wrong, the consequences could be massive. We could end up changing the entire evolution of a planet. It's a huge responsibility.
So the paper has this cool roadmap for terraforming Venus, but you're saying the challenges are just too big, the technology is nowhere near ready, and the risks are too unpredictable. Basically science fiction, right?
I wouldn't go that far. It's not impossible, but it's definitely not happening in our lifetime. Probably not for centuries. The tech hurdles are massive, the energy needs are insane, and there are huge ethical questions.
I see. So terraforming Venus, a cool dream. But for now, it's probably best left in the realm of science fiction.
For now, yes. But who knows what the future holds? Maybe someday, with better tech, a better understanding of planets and ecology, we could revisit this idea. But for now, I'm happy to just admire the creativity and acknowledge how incredibly hard it would be.
So if we're not, you know, booking our flights to Venus anytime soon, what's the takeaway? Should we just give up on this whole idea of making other planets livable?
No, not at all. This paper, even if it's a bit overly optimistic, it still makes us think, pushes us to imagine what we could do if our technology was way better.
Like a giant thought experiment, but for a whole planet.
Exactly. And even if we never actually terraform Venus, just thinking about it could lead to some cool breakthroughs like those super strong materials for space tethers. Imagine what we could do with that stuff in construction, aerospace, all kinds of things.
So it's like this ripple effect of innovation just from tackling a problem that seems impossible.
For sure. And I think there's something deeper here too, something philosophical. When we imagine changing a whole world, it makes us question our own ideas about life, about where we fit in the universe.
It makes you realize that what we have on Earth, the air we breathe, the water, the
Yeah.
stable climate, it's not a given. It's
Yeah.
special. Took billions of years to get here.
Right. And it makes you wonder, do we even have the right to mess with something like that? To try and engineer a whole planet? It's a pretty humbling thought.
It is. Makes you appreciate Earth a lot more, how fragile it is, how important it is to protect what we have.
Exactly. Maybe the biggest lesson from all this isn't about conquering other planets, it's about taking care of our own.
That's a great point. So we might not be moving to Venus anytime soon,
Yeah.
but just thinking about it taught us a lot about ourselves, about Earth, about the universe. That's pretty cool.
It is. It really is.
Well said. And that wraps up our deep dive into terraforming Venus.
Yeah.
A wild idea, inspiring, and yeah, a little humbling. Thanks for joining us. Until next time.